Welcome to this explainer. Today, we're jumping right into Chapter 4, Change of State. We're going to be exploring the invisible, absolutely fascinating physics behind how matter changes state all around us. It's literally nature's ultimate magic trick, and we're going to break it all down for you.
Okay, let's dive into this. Have you ever wondered why a simple puddle of water dries up, or how a single drop of sweat on your forehead actually works as an incredible survival mechanism? Like, why does sweating actually prevent us from getting a heat stroke when it's boiling outside? It's not just basic biology, you guys. There are some seriously powerful physics laws at play here. Here's our roadmap for today. We'll start with states of matter and latent heat mechanisms, take a microscopic deep dive into molecules, check out everyday evaporation and condensation, and finally, we'll tackle a real-world physics application. All right, moving right along to Section 1, States of Matter and Latent Heat Mechanisms. Let's get into it. So, to understand how states change, we absolutely have to talk about latent heat. Latent heat is the energy that's absorbed or released during a change of state. But here's the crazy part. It happens without any change in temperature. The word latent literally means hidden. So you're pumping energy in, but the thermometer doesn't even budge. It just stays flat at the melting or boiling point. It's like the energy goes undercover to get the job done. Let's see how this builds on a heating curve. We start with a solid. Heat it up until it hits fusion or melting, becomes a liquid, and then hits vaporization to become a gas. See those completely flat steps on the timeline? That is exactly where the latent heat of fusion and vaporization are doing their thing. The temperature isn't rising, but trust me, the internal state of that matter is undergoing a massive, total transformation. Section 2, a microscopic deep dive into molecules and energy. Let's zoom way in. Now you might be wondering, if the temperature isn't going up during a state change, what on earth is that latent heat energy actually doing? Well, if we compare kinetic and potential energy, it all makes sense. Temperature is really just the average molecular kinetic energy, basically how fast the molecules are zipping around. But latent heat, that increases the average molecular potential energy. It acts like an invisible hand, snapping the attractive forces between molecules. It's literally like stretching and breaking a rubber band so the molecules can break free from a solid to a liquid or a liquid into a gas. So the crucial point here is that an object's total internal energy isn't just about what the thermometer says. It's the total molecular kinetic energy, the speed, plus the total molecular potential energy, the freedom of the molecules, and then you factor in the mass. The whole shebang comes down to the fact that water at 0 degrees Celsius has way more internal energy than a block of ice at 0 degrees. Why? Because the liquid water has already absorbed that hidden latent heat. Section 3, Everyday Phenomena. Let's bring this back to the real world with evaporation and condensation. When we think of liquids turning into gas, we usually picture boiling water, right? But look at the difference between evaporation and boiling. Boiling only happens at a specific boiling point and needs a major heat source. Evaporation, on the other hand, is super stealthy. It happens at any temperature below the boiling point. Well, actually, scratch that. Any temperature between freezing and boiling, but you get the idea. And here's the kicker. As those fast-moving molecules escape the surface, they steal latent heat from the surroundings. That is exactly why your skin feels so cold when you step out of the shower. The evaporating water is literally robbing heat right off your body. So what speeds this evaporation process up? Well, a higher temperature gives molecules more energy to escape. A larger surface area means more exit doors for them to leave through. And then there's low vapor density or low humidity. By the way, this perfectly explains why a muggy, humid day feels absolutely unbearable. The air is already totally stuffed with water vapor, so your sweat can't evaporate. And if it can't evaporate, it can't take the heat away. And this brilliantly illustrates the flip side of the coin, condensation. When warm vapor meets a cooler surface, it dumps that latent heat it was holding onto and turns right back into a liquid. This solves those little everyday mysteries, like, how a glass of iced tea gets all wet on the outside, or why your glasses fog up when you eat hot noodles. The glass isn't leaking, it's just water vapor in the air, hitting a cold surface, releasing its latent heat, and condensing. Moving right along into Section 4, Physics Application Practice. Let's put all this theory to the test. Okay, let's slow things down a bit and walk through a real textbook problem together. Meet Yvonne. She's 50 kilograms, she's working out hard, and she sweats out 650 grams of water. That's 0.65 kilograms. Here is the big mathematical mystery. When all that sweat completely evaporates off her skin, exactly how much energy is taken away from her body? Let's figure it out. To solve this, we need a massive, absolutely crucial constant, the specific latent heat of vaporization of water. It takes a whopping 2.26 million joules of energy to evaporate just 1 kilogram of water. This huge number is the secret key to unlocking the math behind our body's amazing cooling system.
Let's break this down into 2 simple steps so we don't get overwhelmed. Step 1, we calculate the energy removed using the formula Q equals M times L. We multiply her 0.65 kilograms of sweat by that massive 2.26 million joules, and we get 1.47 million joules of energy. That is how much heat the sweat pulls away. Now, step 2, let's try a crazy hypothetical. What if that heat wasn't removed? We'd use the formula Q equals MC delta T to see how much her body temperature would change.
Now, what's really interesting about this slide is the result. If that 1.47 million joules of energy wasn't removed by evaporation, Yvonne's body temperature would literally spike by 8.39 degrees Celsius. Normal body temp is around 37 degrees, so adding almost 8.4 degrees puts her over 45 degrees Celsius. Medically speaking, there is no way you survive that. It's a fatal heat stroke. Without the massive latent heat of vaporization of water, we'd never survive a simple workout.
So, what does this all mean? It means physics laws aren't just boring equations you memorize. They are the invisible, life-saving rules governing everything we do. From Chapter 4 straight into your daily life, it's all connected. So, I leave you with this. The next time you're out on a hot day and feel a drop of sweat on your forehead, will you feel the absolute power of those microscopic molecules keeping you alive? I bet you will. Thanks for hanging out with us on this explainer, and we'll see you next time.